I'll go and start looking at this problem. So again, it starts with the zeros of the function. The zeros, that's a fancy way of saying the x-intercepts. There's only one big difference between zeros and x-intercepts. Zeros would literally just be -3 and 1. It's like an x equals equation. The big difference between that and an x-intercept would be an actual ordered pair. -3, 0, and 1, 0 would be my ordered pairs that show the x-intercepts. That's the difference between a 0 and an x-intercept. It's a very small difference, but it still is a difference. Finding the maximum value, that's where we're looking for this top of this parabola, and the y value happens to be 4. And if we were looking for the vertex instead, we would say it's -1, 4. So the vertex is the ordered pairs that make up the actual vertex. The maximum value would be the y value of the vertex. At y equals 4, that's where we're hitting the maximum value. Okay, so another equation type problem. The next one says the standard form of any quadratic, any quadratic, is going to be written as what? As y equals ax squared plus bx plus c. All right, that's just our standard general form. That's what we use for the quadratic formula or something like that. All right, problems 4 and 5, go ahead and graph the function. So problem 4 is in vertex form for me, if I remember this correctly from last year. From AGS2, I can see, hey, there's the vertex right there. I'm going to need to label my graph, though, real quick. We'll go ahead and label it. Count it by ones. And for this point, I see the point 1, 4. That's going to be my vertex. And then it's going down pretty quickly from there. It's going to go down something like that, and then something like that, and then we can go ahead and sketch a parabola. Again, you can use Desmos to do this, and that's what this one's going to look like. But the key is we should be able to identify the vertex, because this is in vertex form, as 1, 4. And then the axis of symmetry is just a label as well. Axis of symmetry is always the line that cuts the parabola perfectly in half. And it's always going to be the x value of the vertex. In this case, it's x equals 1. That would be the axis of symmetry part. Okay. The second equation here is not in vertex form, that's in factored form, or we can think about it as intercept form. We can see the x-intercepts here. There's an x-intercept at 2, 0, and an x-intercept at -3, 0. I'm going to go ahead and label this. And now this one, I can see those two values. I know the vertex is going to be down here somewhere. It's actually going to be like way down at like -18 or something. And our function is going to look something like this. And again, you could use Desmos to do this. I could adjust the scale to make it a little bit better. And this time it turns out that the axis of symmetry is at like x equals -1/2, I think. And the vertex we should be able to find is like -1/2, I think it was 18. I could be mistaken. I don't have it directly in front of me. But that's the idea for this particular problem. All right, the last 3 problems. We talked about number 6 already. You just create the factor box and you're trying to write it down that way. Problem 7 we can do very similarly. And I'll say x squared. There's a 0x in the middle and then a -16. And x times x is just x squared. And because there's a 0x, these have to be the same number, and the number would be 4. -4 and +4 is going to get me 16. And that's because I get -4x and +4x in the middle, and that adds up together to get 0x. So this becomes factored form x plus 4 and x minus 4. The one part we don't want to forget about is it says find the x-intercepts. So we've got this in factored form. To find the x-intercepts, we're going to solve for x. We have to say this whole thing equals 0. And then I can write two separate equations. This is very much like something we did in the logarithms unit last unit, right? Some prior knowledge information here. And we get x plus 5 equals 0, x plus 4 equals 0, and I'm going to subtract 5 and 4 from each side respectively. And I get x equals 5, x equals 4. So my x-intercepts would be 4 comma 0 and 5 comma 0. Those would be the x-intercepts. When y equals 0, x equals 5, or x equals 4. Okay.
Negative 5 and negative 4.
Thank you. Negative 5 and negative 4. Way better. Good catch. Negative 5 and negative 4. Yes. And I could graph that to verify. I would double check that on the graph. So to find the axis to symmetry and the vertex in question 5, all I did is I graphed it on Desmos, and then I just looked for the vertex on the graph on Desmos. Okay, that's what I would say for number 5. All right, problem 6, same thing where I get, or problem 7, I set it equal to 0, and I get two separate equations, x plus 4 equals 0, x minus 4 equals 0, and I get x equals negative 4, so negative 4 comma 0 is an x-intercept. X equals positive 4, so positive 4 comma 0 is an x-intercept. Last one, number 8. Hopefully I can factor this one, but I'm not sure if I can. But we'll give it a shot first. 2x squared plus 5x minus 3. If there's a 2x in the first number, that means one side's going to be 2x, one side's going to be x. All right? Because then x times 2x equals 2x squared. Now, negative 3 can be two things. It can be 3 and 1. So I can try like a 1 over here and a 3 over here. It's a negative 3, so one of them is going to be positive, and because the 5 is positive, I'm going to do a positive 3 there. 3 times 2x is a positive 6x. X times negative 1 is a negative 1x. And hey, look at that. That worked out. First guess, I got lucky. But it works. It gets 2x minus 1 and x plus 3. And there's my factored form. All right, so factoring quadratics. What we're going to be looking at this unit specifically is more than just quadratics. We're going to be looking at polynomial functions. We'll talk about what those are today. And how do we tackle those types of problems. So this one was 2x minus 1 equals 0. Add 1 to both sides, divide by 2. You're going to get x equals 1/2. The other one, x plus 3 equals 0. Subtract 3 from both sides, you're going to get x equals negative 3. So negative 3 comma 0 is an x-intercept. 1/2 comma 0 is an x-intercept. So what we're starting with today is identifying polynomial functions on worksheet number 18 here. So first thing I want to talk about is something called a monomial. A monomial is an expression that is a number, a variable, or the product of a number and one or more variables. So 3 is a monomial, it's just a number by itself. X is a variable by itself, or 5 times y. That would be 3 examples of a monomial. What a polynomial is a monomial or sum of monomials. So once you have a sum or subtraction, addition or subtraction, now you're talking about a polynomial function. So a quadratic function, ax squared plus bx plus c, is a classic example of a polynomial. It's just and we're going to talk about what type of polynomial it is. It is called a quadratic, but yeah. That's what we're going to be looking at today. A polynomial function is going to be in this form here, and this equation looks pretty intimidating. It's a sub n x to the n power plus a sub n minus 1 to the x n minus 1 power plus ... etc., etc. Let's break it down, though, what this actually means. It looks intimidating, but it's not too bad. First, we'll start with this a sub n. A sub n is what we're going to call the leading coefficient. All right, it's just whatever number is with the highest exponent. And we'll talk about that a little bit more as we go through class today. The leading coefficient has to be a real number. And it cannot equal 0. Because if that number equals 0, you're just going to have 0 times x to the whatever power. And then you would just get 0. So it cannot equal 0. Okay, so we always want to focus on the leading coefficient. That's one thing we want to focus on in any polynomial. We want to focus on the exponent, specifically this n. N is the degree of the polynomial. All right. And some important things about n. N is the largest positive comma integer value. I'm going to say valued exponent. All right, so that's really important, the largest positive integer value exponent. And what that means is we can only have whole numbers for exponents. We want no fractions and no negatives. Which is different than what we did in logarithms, because when we were doing the logarithms unit, we're solving for exponents. We could have exponents that were fractions, and we could also have exponents that were negative numbers. Now, when we're talking about these polynomial functions, we don't want to deal with that anymore. So like x to the negative 2, x to the 3 halves, anything like that, we want to say, well, no fractions and no negatives. So those are both examples that would just be, nope, we can't do that. Okay, we don't want to see any negative exponents. We don't want to see any fraction exponents when we're talking about polynomial functions. If we ever see anything like that, it's not really a polynomial function. Okay. Last thing to talk about from this equation up top is this last number, a sub 0. A sub 0, or a naught, that is called the constant term. It's the c value from a quadratic, ax squared plus bx plus c. All right. So just to note, this equation is just representing a polynomial in standard form. It's not in factored form, it's not in vertex form. This is just the equation for a polynomial in standard form. Okay. And that last number, the a sub 0, the constant term, or the c value from quadratics, that actually is an important number for us. It represents the y-intercept. Zero comma a sub 0 is going to be our y-intercept every time. And that's just because if I plugged in 0, everything's being for x, everything's being multiplied by x except for the last number. So that last number would just be our constant term. It'd be the only thing left. Okay, plus that number. Okay. Any questions so far? We're going to talk a lot about this equation today and how to break it down. We're going to do some examples of it right now. All right, a polynomial is in standard form if its terms are written in descending order of exponents from left to right. So descending order means we start on the left side, go to the right side. And that's descending order of exponents. All right, so some examples of standard form. We're going to talk about the degree of the polynomial. Okay, so degree 0 is going to look like this. Just the constant term, a sub 0. And an example of that would be like a 4. I don't know, something like that. A linear function, we should know that. A linear is like that mx plus b equation, except we're going to write it a little differently today. We're going to write it as a sub 1 x to the first power plus a sub 0. And again, x to the first power, that's why this is a degree 1 polynomial, because we can recognize the degree by finding the highest level exponent. An example of this might be 3x plus 5. That's a good example of a linear function. A quadratic function, okay, would probably look like a sub 2 x squared plus a sub 1 x to the first plus a sub 0. Or we might recognize that as like ax squared plus bx plus c. So here's an example, negative 2x squared minus 5x plus 7. Notice that with the quadratic function, there's the degree 2. It's saying it's something squared, right? And I don't have to write the degree 1. Like when it was 3x, I didn't have to say 3x to the first power. When it was 5x, I didn't say 5x to the first power there. All right, there's a couple things to keep in mind there. And we can keep building these things. A cubic function would be a sub 3 x to the third plus a sub 2 x squared plus a sub 1 x to the first plus a sub 0. Hopefully we're starting to see a little bit of a pattern here. And a good example of a cubic function, x cubed minus 6x squared plus 2. We're not going to write an x value in this one. Sometimes they don't have x values. And that's just because it'd be like x cubed minus 6x squared plus 0x, but we don't need to write 0x plus 2. All right, but that's kind of what a cubic function would look like. Last one, a quartic function. That's a degree 4 polynomial. That's going to look something like a sub 4 of x to the fourth plus a sub 3 x cubed plus a sub 2 x squared plus a sub 1 x to the first plus a sub 0. Hopefully that pattern makes sense to us. A good example of something like this, 2x to the fourth minus x cubed plus x squared plus 3x minus 19. Something random like that. but it always goes in what's called descending order. It goes from the fourth power to the third power to the second power to the first power, and then x to the 0 power we don't need to write down. And we can tell it's a fourth degree polynomial because of the 4 right there at the very front. That's our fourth degree polynomial. Okay, what I want you guys to do now is go ahead and write down a fifth degree polynomial for us. So what would the fifth degree polynomial look like with the a's and the x's? And then go ahead and provide an actual example of what a fifth degree polynomial would look like. All right, so I wrote down real quick a fifth degree polynomial. I did it in blue, so a sub 5 x to the fifth plus a sub 4 x to the fourth plus a sub 3 x to the third, a sub 2 x squared plus a sub 1 to the x, a sub of x, and then plus a sub 0. And then I just wrote down an example of a fifth degree polynomial. And actually I did not write down a good example. What I'm going to want to do for an example, like maybe y equals 3x to the fifth minus 7x squared plus 5, something like that, where I need to have the highest degree, the fifth degree in there, and then I don't necessarily need the fourth or the third or the second or the first. I could just say, hey, this is 0x to the fourth, 0x to the third, it's negative 7x squared plus 0x to the first plus 5. So, I mean, that's how I could kind of work this type of problem, something like that. Okay. Now, there are 4 problems down here I'm going to ask you guys to work on. And it says, for problems 1 through 4, do the following. First, decide whether the function is a polynomial function. So you're going to write yes or no. Yes, this is a polynomial function. No, this is not a polynomial function. If it's not a polynomial function, you'll explain why. If it is a polynomial function, you'll skip the explain why. You're going to write it in standard form, which is reordering it from the greatest degree exponent to the least degree exponent. And then if yes, you're going to state its degree as odd or even. And you're going to identify the leading coefficient. All right, so that's some big vocabulary there. It's not too bad, though. Odd or even just means once we determine the degree of the polynomial is the degree number an odd or even number. If we go back up here, degree 1, that's an odd function. Degree 2, that's an even. Degree 3, odd. Degree 4, even. Degree 5, odd. That's what odd or even is. You're just looking at the first exponent, and you can determine whether it's odd or even. Leading coefficient is whatever number is in front. So there's a 2, there's a 1, there's a negative 2, there's a 3. Those are your leading coefficients. All right. So again, go ahead and work on these 4 problems now. Take a couple minutes. Ask questions if you're confused by something, but this is new vocabulary for us, but hopefully we got a good idea of it. All right, so take a look at these ones. So problem 1, again, looking at exponents, I see a fourth power, a second power, and then this would be like x to the 0 power. So this one, yes, definitely a polynomial function. I don't see any negative exponents. I don't see any exponents with fractions in them. So now I can skip to the third part. Write it in standard form. So that's from the greatest degree to the smallest degree. This one is actually already written in standard form. So that part's done for us. And then the last part, state the degree is odd or even. So 4 is the highest degree. That's an even number. And then the leading coefficient, what's the number in front of that exponent? Turns out the leading coefficient in this one is just the number 1, because there was no number written in front of the x there. So just the number 1. That's what we're doing here. Second problem, I see an x to the first power. There's no exponent there. This looks like a constant term, x to the 0 power. And then I see an x squared. So this one is also a polynomial. Sure is, just looking at those exponents. Write it in standard form. It's going to be g of x equals pi x squared plus 7x minus square root of 3. It's an x squared, so this one's an even degree polynomial, and the leading coefficient is pi. All right, because pi is a number, that's our leading coefficient. Okay. Problem number 3, 5x squared, 3x to the negative 1 right there, negative 1. That means this one is a no. And we cannot have negative exponents for a polynomial function. And then the last one, I kind of mentioned this already, you have 2 to the x power. So the answer for this one is no. And that's because x is a variable. A variable that we can change into a negative number or a fraction. So that's what you would do with problem 4 here, just because there's a variable fraction, okay? Any questions on those 4 problems before we move on? Okay, good. Let's take a look at this part then, the last part today. We're talking about odd degree versus even degree polynomials, which we just kind of brought up a minute ago. This is what odd degree versus even degree looks like. Big thing we'll start with is we have this y equals x. I'm going to go ahead and highlight all the odd degree with red here. I'll highlight all the even degree polynomials with blue. Okay. And what we're going to start talking about is something called end behavior. We're going to focus on this more next time as well. But basically, end behavior is determined by 2 things. It's determined by odd or even degree polynomials. It is also determined by the leading coefficient. Those 2 things are going to help us talk about end behavior. Today we're not going to focus on the second part. We're going to focus on this first part. Odd versus even degree. That's what I want to look at today. Next time we'll talk more about the second part. But looking at these problems here, notice the odd degree. On the left side of the graph, it starts in a negative direction, and on the right side, it's in a positive direction. That's what end behavior is. It's like what's happening way off the graph, what's happening to this function as it keeps going on. Because technically, these functions do go on forever. So I'll put arrows on all of them. They all go on forever, even though they don't have arrows drawn on them right now. And what we should notice is there's something different going on with the odd degree versus the even degree. The odd degree, on the left side of the equation, so to speak, they're coming from a negative direction, and they're going to a positive direction on the right side. That's what these odd degree polynomials look like. The even degree, notice on the left side they're coming from a positive direction. On the right side they're also going to a positive direction. So all the even degrees look like these parabolas, that U shape. Like what we saw with quadratics last year, you would always see that U shape. All right. And that's what I mean by determining by odd or even degree polynomial functions. If you can determine a function is odd versus even degree, it's going to help you describe the end behavior, what's happening way on the extremes of the graph to this function. Okay, that's the idea there. Okay, so a quick note, we can say odd degree polynomials will always have end behavior that go in opposite directions. And what I mean by that is on the left side it's going in a negative direction, on the right side it's going in a positive direction. There are ways for it to go from positive to negative from left to right, and we're going to talk about that next time. That has to do with the leading coefficient. Okay. Even degree polynomials, both left and right end behavior go to the same direction. Okay. Both left and right. Sorry, I'm out of room here. End behavior in the same direction. Okay, that's the idea with with these last couple problems here. All right, just one question to clarify on problem 2, when we're looking at rewriting this in descending order. So we started with this g of x equals 7x minus root 3 plus pi x squared. When we rewrite it in standard form, that's where we have to write it in descending order, which is highest degree exponent, second degree, then the first degree, and then the 0 degree. That's what descending order means. And the way we determine what the leading coefficient is, it's whatever number is in front of the x. And in this case, the number that was in front of the x happens to be pi. Pi, which is a number, it's the number 3.14. And that's why the leading coefficient for problem number 2 was pi. That's just to clarify a little bit more on that particular problem. Okay.